Hello everyone, I am Mitra. In previous video, Deepal explained you about the basic of method validation. So you learn about the introduction of method validation, what is the purpose of method validation. Now in this video, we will start method validation in details. So when we start the method validation, first of all we required reference standard or working standard and internal standard. So, what are these standards? So, reference, working, and internal standards are nothing but the drug in the powder or liquid form. For example, if we have clinical study of nebivolol, then we need the reference or working standard of nebivolol in the powder form or liquid form, whatever is available. Now, we will understand the reference difference between the reference standard, working standard, and internal standard. So, first of all, what is the reference standard? So, reference standard is the highly characterized material suitable to test the identity, strength, quality, and the purity of the substance for pharmaceutical use and medicinal product. So, this is the definition of the reference standard. So basically, if we say reference standard are the standards of the highest purity and which are available from the pharmacopoeias like US pharmacopoeia, European pharmacopoeia, British pharmacopoeia or Indian pharmacopoeia. This reference standard have the purity of generally more than 99.5 percentage. Now, what is working standard? So, working standard is a drug substance of a established quality and purity as shown by the comparison to the reference standards. So, purity and quality of the working standards are determined based on the comparison with the reference standards. And these working standards are generally available from the commercial suppliers like ClearSynth or TRC, any one of the commercial suppliers. So in our study, we generally use the working standard as per our requirement, and we outsource it from the commercial suppliers. So in our study, either we can use reference standard or working standard, both of them. Now we will learn about the internal standard. What is internal standard? So internal standard is a known concentration of a substance that is present in every sample that is analyzed. Now internal standards are also commercially available from the suppliers like ClearSynth, TRC or V1 like this. Now what is the purpose of adding the internal standard to our subject sample? So basically if we say it is used to correct for variability due to the analyte loss during sample analysis. I will explain you this case by taking a simple example. Let's take the one case in which we don't add the internal standard in the unknown subject sample. So, if we analyze this sample without internal standard and if there is any mistake happen during analysis, so at the end we will not know that if there is any mistake during analysis. Why? Because our subject sample is unknown concentration. In plasma, we don't know the concentration of the sample in the subject sample. So at the end, instead of 100 nanogram, if we get 50 nanogram of the concentration in the subject sample, we will not know that because we don't add internal standard. And in the other case, if we add internal standard during sample analysis, so in this case, if there is any loss during sample analysis, so in this case there will be loss of drug also and there will be loss of internal standard also. So in this case, at the end, if there is any error during sample analysis, we will come to know that. Why? Because we have added the known amount of concentration of the internal standard in the subject sample. So if there is any loss in internal standard, so we can say that there may be also loss during subject sample analysis of the analyte. So we can identify this sample and we can repeat this sample. Sometimes you hear that the sample is repeated due to the internal standard variability. So these are these samples that have any mistake during the original sample analysis. Now, what is the requirement of the reference standard? As per the regulatory requirement. So, reference standard must have the certificate of analysis, that means COA. And what does this COA should have? This COA must have the information like batch number or lot number, purity of the reference standard, and expiration date of the reference standard. So, the COA of reference standard or working standard should have all of this information as per the regulatory requirement. The next thing is that require the source of the reference standard and working standard. So, from where we purchase this working standard or reference standard, we should have documented this thing. The next thing is required that record of the receipt, usage and storage of this standard. So whenever we receive this standard, we should record the date of this receipt, then usage of this and storage of this, as because storage temperature is having a great impact on the stability or in the purity of the working or reference standards. So we should store the reference standard or working standard as per the temperature which is mentioned in the COA. Generally in the COA, storage temperature is also mentioned, and if it is not mentioned, then we should ask the supplier or who supplied to us reference standard that what is the storage temperature of this reference or working standard. And the same about this thing is applicable for the internal standards also. Now you must be thinking that what is the usage of this reference standard or working standard. So usage of reference standard is to that preparation of the calibration curve, that means CC, and quality control samples, that means QC. I will explain regarding the calibration curve and QC sample in the later part of the video in details. So this is just an example. This addition of the known amount of reference standard or working standard. This is the, for example, this is as a test tube. This is the diluent, and this diluent is approximately 1 ml. And if I make the stock solution of 1 mg per ml, that means in 1 ml I have 1 milligram of reference standard. That means 1 million nanogram per ml. And from this, if I want to prepare the working solution of 10,000 nanogram per ml, then I require 0.1 ml of stock solution in the 10 ml diluent. This calculation I will explain you in the later part of this video. Now I will explain some details about the internal standard. You must be hearing about the internal standard, that stable isotope label or structural analog that is non-labeled. So what is this? Now I will take the example of metronidazole. So this is the chemical structure of the metronidazole. And so you can say this is the working standard of the metronidazole. And we have two choices for choosing the internal standard. Either we can choose stable isotope label internal standard, or we can choose structural related compound, the analog, that is non-labeled internal standard. So I will explain this to you by example. Now this is the stable isotope labeled internal standard, that is metronidazole D4. Now what does this mean, D4? So in this metronidazole D4, generally this hydrogen, you can see here in metronidazole structure, there is one hydrogen here, and one hydrogen here, and one is here. So there are total 4 hydrogen. So these 4 hydrogen are replaced by the deuterium in this metronidazole D4. So this is the more stable you can say, because in this internal standard the hydrogen is replaced by deuterium. Now, if we take the example of the structural related compound analogs, or that is non-labeled standard, that means ornidazole. We can also choose the ornidazole as internal standard, because this have the similar structure as of metronidazole. Just the change is here in this chlorine group. You can see all the structure is the similar. So either we can choose metronidazole D4 or ornidazole as the internal standard. But there are some advantages of choosing the metronidazole D4, that is the stable isotope label. What is the advantage? So by using this internal standard, we can get better accuracy and precision. But the thing is that this internal standard is more expensive compared to this internal standard. Now this internal standard is nothing but the working standard. This means this is the API of the ornidazole. So this is the reason why this is cheap and why this is more expensive. Now we will learn about the calibration curve. First of all, what is calibration curve? So calibration curve is the relationship between the instrument response and the calibration standard within the intended quantization range. Now before starting any validation, we should decide the range of the calibration curve. So how we can decide the range of this calibration curve? So we can decide the range based on the Cmax of the drug. So to decide the calibration curve range, we will do literature search and we will find the previous clinical studies or previous bioequivalent studies of the similar compound, and then based on this we can find the Cmax. So this Cmax will be the approximate Cmax. We will not take the exact Cmax. Let's say for example, in certain drug the Cmax is 50 nanogram per ml, which is approximately. So how now we will decide the calibration curve range? So our upper limit will be at least 1.5 to 2 times of the Cmax. So that means here we will take the 2 times. So it will be the 100 nanogram per ml. That means ULOQ. This is called upper limit of quantification. And so this is called as a standard 8. I will explain this standard 8 and regarding standard 1 in the later part of the video. And how we will decide the lower limit of this calibration curve range. So lower limit is, should be at least less than 5% of the Cmax. So if we calculate the 5% of the 50 nanogram, then it will comes around the 2.5 nanogram per ml. But generally we try to keep our lower limit of quantification as low as we can. It is based on our method also, and it is also based on the response of our instrument also. So here I will take it 1 nanogram per ml, which is called LLOQ. That means the lower limit of quantification, which is standard 1. So in this case, our range is from 1 nanogram to 100 nanogram per ml. Now, as per regulatory requirement, minimum 6 level of the calibration curve is required. That means what? That means at least we require standard 1, 2, 3, 4, 5 and 6. But generally in our practice we take 8 standard. In addition to this 6 level of calibration standards, we also require the blank samples and zero samples. Now, this blank sample and zero sample is not the part of the calibration curve, but these two samples should be run before running the calibration curve. So now what is the blank sample? So blank sample is processed matrix sample without analyte and without IS. IS means internal standard. So blank sample is the sample which does not have analyte or internal standard. And what is the zero sample? So zero sample is the processed matrix sample with IS, that means with internal standard. So the difference between the blank and zero sample is that blank sample does not have analyte and internal standard, while the zero sample have only internal standard. So this is the main difference between the blank sample and zero sample. Now you must be thinking that what is the need of these samples? So these samples are generally needed to determine the carryover. Now you must be thinking that what is carryover now? So carryover is the appearance of an analyte in a sample from the preceding sample. This is just the definition of the carryover. We will explain the carryover in details in the later part of our sessions of method validation. Now, what is the acceptance criteria for this calibration curve as per the regulatory requirement? So the back calculated concentration of the calibration curve should be within the plus minus 50% of the nominal value, except for LLOQ, for which it should be plus minus 20%. Now, I will explain you this in a simple word. Now, our range, you see that our LLOQ and LLOQ is 1 nanogram and ULOQ is 100 nanogram. Now, as per this sentence, the calculated concentration of the CC should be plus minus 15% of the nominal value. That means the nominal value of our ULOQ is 100 nanogram. Okay, but during preparation, we cannot say that we will get 100 nanogram per ml, because there are several factors which will affect the measuring of this concentration. So maybe we can get 101, 102, or maybe we will get 95. Maybe we will get 110. So as per the criteria, plus minus 15% is accepted. So from 100, if we get 115, then it is accepted. If we get 85, then it is accepted. But if we get 84, then this is not accepted. If we get 116, then it is not accepted. So this can be ranging from 85 to 115. Now, except for LLOQ, for which it should be plus minus 20%. Now, for LLOQ, it can be plus minus 20%. That means it can be ranging from 1.20 to 0.80. So that means 0.80 to 1.20. Then at least 75% of the calibration curve should pass the above criteria. Now we see that minimum 6 level of the calibration curve is required in the calibration curve. So that means at least 75% of this calibration standard should pass this criteria. In our case, generally we take 8 calibration standards. That means from 8, at least 6 calibration standard should pass this criteria. Moreover, there is also the acceptance criteria for blank and zero sample. Now what is that criteria? So area in the blank and zero sample at the retention time of analyte should be less than 20% of the area of LLOQ. And for the area in the blank at the retention time of the internal standard should be less than 5% of the area of the lower limit of quantification sample. This criteria I will explain you by example in the later part of the method validation experiment. Now, quality control sample, that means QC. Generally we have 3 levels of the QCs, that is low QC, mid QC and high QC. Now, as per the regulatory requirement, the low QC should be 3 times of the lower limit of quantification. Mid QC should be around the 30 to 50% of the ULOQ, and the high QC should be at least 75% of the ULOQ. I will explain this all calculation in the later part of this video. Now, what is the acceptance criteria of the quality control sample? So, at least greater than or equal to 67% of the QC should be plus minus 15% of the nominal value. As I explained you in the previous part of that calibration curve, the same criteria applies here, that plus minus 15% of the nominal value. Greater than or equal to 50% of the QC at each level should be plus minus 50% of the nominal value. So this is the basic thing about the quality control sample. Now, calibration curve and QC sample should be prepared from the separate stock solution. So we should use the separate stock solution for preparation of quality control sample and calibration curve sample. So I previously show you that how to prepare the stock solution. So we should prepare 2 stock solutions like this, one for calibration curve and another for quality control sample. Another thing is that calibration curve and QC should be prepared in the same matrix as the matrix of the intended study sample. That means if our study samples are in plasma, then our calibration curve and QC sample should be prepared in the plasma. If our study samples are in blood, then our calibration curve and QC sample should be prepared in the blood. Like this, there are example of urine. Some of the drug we measured in the urine. So we should prepare the calibration curve and QC sample in the urine. Now I will explain you that how to decide the calibration curve and quality control sample concentration. Now let's say for example that our range of the calibration curve is 1 to 100 nanogram per ml. That means our LLOQ, that means lower limit of quantification, is 1 nanogram per ml, that is called standard 1. And here our ULOQ, that means upper limit of quantification, is 100 nanogram per ml, that is standard 8, that is ULOQ. So first of all we decide these 2 standards, standard 1 and standard 8, that is LLOQ and ULOQ. Now we will decide our concentration of the QC samples. So first of all, before deciding these values, we will decide the concentration of the QC samples. Now in the guidance it is mentioned that the low QC should be 3 times of the LLOQ. Okay, so now what is our LLOQ? Our LLOQ is 1 nanogram per ml. So 3 times of the LLOQ means 3 nanogram per ml. So our low QC will be 3 nanogram per ml. Now we will decide mid QC. As per the regulatory requirement, mid QC should be at least 30 to 50% of the ULOQ. Now in our routine practice, generally we take mid QC at the 50% of the ULOQ. Now what is our ULOQ? ULOQ is 100 nanogram per ml. So we will choose our mid QC at 50 nanogram per ml. Now we will decide the high QC concentration. High QC concentration, as per the requirement, it should be at least 75% of the ULOQ. Now in our routine analysis practice in method validation, we take 85% of the ULOQ. That means our high QC will be 85% of the ULOQ, so it will be 85 nanogram per ml. So now we have decided the QC concentrations, our LLOQ concentration and ULOQ concentration. Now we will determine the concentrations of the standard 2, 3, 4, 5, 6 and 7. So generally we take standard 2 at the 2 times of the LLOQ. That means our LLOQ is 1. So our standard 2 will be 2 nanogram per ml. Now one thing to keep in the mind that our quality control sample concentration and the calibration curve standard concentration should not be the same. So now our low QC concentration is 3 nanogram per ml. So our calibration curve standard should not be 3 nanogram per ml. Like the same thing, no any of our standard should be have 50 nanogram or 85 nanogram per ml. So now we will try to keep our standard 3 in between the low QC. Low QC will be in between the standard 2 and standard 3. We will try to keep this gap between standard 2 and 3 as low as possible. To understand this thing, actually we have to go into the more details that why this difference, this distance should be less, because the accuracy of the low QC should be plus minus 15%. So now we have decided standard 1, 2 and 3. Now we will decide the standard 7. How we will decide this standard? Based on our high QC sample. Now if you see that the difference between our standard 8 and high QC is 15. So again we will subtract the 15 from 85. So we will get 70. So our standard 7 will be 70 nanogram per ml. Now we will decide standard 6. How we will decide standard 6? Again the same method. We will decide the difference between standard 7 and mid QC. That is, this difference is 70 minus 50 is equal to 20. So same thing we will do. We will subtract the 20 from the 50. So we will get 30. So our standard 6 will be 30 nanogram per ml. So now we have concentration of standard 1, 2, 3, 6, 7 and 8. Now how we will decide the standard 4 and standard 5 concentration? So this concentration will be anywhere between standard 3 and standard 6. So standard 4 we will keep 10 nanogram and standard 5 we will keep 20 nanogram. Now actually there is no any criteria that how we will decide standard 7, standard 6, standard 5, standard 2, 3, 4. Just there is criteria to decide standard 1 and standard 8, and there are some criteria to decide the QC. You can keep your standard 2 to standard 7 anywhere in between this 1 to 100 nanogram. But this is whatever the procedure I have explained you that we are using in our academia biocenter. Now I will explain you about how we prepare the calibration curve standard samples in the plasma. As I told you previously that I will explain you this calculation in the later part of this video. So now I will explain you this calculation, how we do this. Okay, first of all, our stock solution concentration is around 1 million nanogram per ml. As you see here, we prepare the stock solution of 1 million nanogram per ml. How we prepare it? That I explain you that we add 1 milligram per ml of the reference or working standard in the diluent, and we get the concentration of 1 million nanogram per ml. This diluent may be methanol or acetonitrile or water, any diluent that is in which drug is can be diluted. So now we have stock solution with concentration of 1 million nanogram per ml. Now from this I want to make working solution of 10,000 nanogram per ml. Okay, so now how I will decide that how much amount of or how much volume of the stock solution I need to get the 10,000 nanogram per ml. So this is we can understand by this formula. Okay, so for working solution N1V1 is equal to N2V2. Now N2 we know that N2 is we want to get 10,000 nanogram per ml concentration. So here N2 we will keep as a 10,000 nanogram. Okay, then V2 means volume. So how much volume of working solution we need? So we can say that we need 10 ml. So here we will put 10 ml. And N1, we know that N1 means our initial concentration of stock solution, which is 1 million nanogram per ml. So here we will keep 1 million nanogram. Okay. So if we solve this equation, we will get 0.1 ml. So here you can say that to get the working solution of 10,000 nanogram per ml, we need to take 0.1 ml of stock solution and dissolve it in 10 ml of diluent, and then we can get 10,000 nanogram per ml of working solution. So here I tell you that here we take diluent of 10 ml, and we from this solution we take 0.1 ml of stock solution, and from 0.1 ml of stock solution we add in this and make up the volume up to 10 ml. So we will get the working solution of 10,000 nanogram per ml. Now from this working solution, actually we need to prepare serial solution. I will give you example for just standard 8, that is ULOQ. Like the same we prepare for standard 1, standard 2, 3, 4, 5, 6, 7, as well as low QC, mid QC and high QC. So there is serial solution for each standards. Like there is serial solution for standard 1, there is serial solution for standard 2, 3, 4, 5, as well as there is serial solution for low QC, mid QC and high QC. So how I will prepare serial solution from working solution? So the same formula will apply here, that for serial solution N1V1 is equal to N2V2. Now our N2 is 1000 nanogram per ml. V2 is the 10 ml, that we will take 10 ml diluent, and our N1 is 10,000 nanogram per ml. If we solve this equation, we will get 1 ml. So 1 ml of working solution required to prepare 10 ml of serial solution having the concentration of 1000 nanogram per ml. So from this we will take 1 ml and dissolve in 10 ml, and we will get 1000 nanogram per ml. Now the final stage, that how we prepare the plasma sample. The same way, but in this we will take plasma instead of the diluent. Here we will take diluent, as I tell you previously that diluent may be methanol, water or anything else. But here we will take plasma. I explained you previously that CC and QC should be prepared in the same matrix as the matrix of the intended study sample. So here we have to prepare the calibration curve and QC in the plasma. So to prepare 100 nanogram per ml of standard 8, as I explained you previously that our standard 8 is 100 nanogram. So how I can prepare this standard 8? Same equation we have to apply for plasma samples also, that N1V1 is equal to N2V2. Now our N2 is 100 nanogram per ml, and we will take 10 ml of plasma. So here I will keep 10 ml, and here 1000, that is the initial concentration of serial solution. So it is 1 ml. That means what? I need to take 1 ml of serial solution and then dissolve it in 10 ml of plasma, and resulted I will get 100 nanogram per ml of the plasma, that is standard 8. So here I give you example of standard 8 how to prepare. Similarly we can prepare standard 7, standard 6, 5, 4, 3, 2, 1 as well as QCs also by using the same equations. Now I will explain you the basic, very basic of how we prepare calibration. What is calibration curve? So this is basically calibration curve. This is the calibration curve. This is concentration, and this is instrument response. This is our calibration curve, and this dot are the calibration standards. You can say this. So first of all, we have to run the calibration curve in calibration standards in our LCMS. So this curve will be plotted based on the concentration of the calibration curve, and then this QC is represented as cross here, and then this is unknown concentration, unknown sample of the unknown subject sample. So we can determine the concentration of this unknown subject based on the calibration curve by using this equation, that is y is equal to mx plus c. Actually in this we can have whole lecture, but this is the very basic thing I explained you here. So here in this equation, m is the slope, c is the intercept, and y is the instrument response. So we can get x, that is the concentration of the unknown sample. So if we know all this value now, we can determine the concentration. Actually this all the calculation is done in the analysis software in LCA, which is installed on our computers in BA lab. So we do not have to do all this calculation, but this is just as a basic, that how in the analysis software this calculation is done. So this is the basic. Now I explain you about reference standard, working standard, internal standard, and calibration curve and quality control samples. So now in the next video we will go through the experiments of the method validation sample. Sorry for interruption. Actually there is a siren at 6 o'clock due to coronavirus lockdown. So here this you understand the basic and what is reference standard, internal standard, all the things. In the next video we will explain about the experiments of method validation. Thank you so much all of you.